Dear Lavanya, please kindly mute your mic. Hello.
Hello. Noise is coming. Yeah. So as you already have heard that classical computer is 1 or 0, but in place of quantum computer, actually it is a probabilistic things. It is not exactly 1 or 0. It is a probabilistic value, but based on the probabilistic value, we consider whether it will be towards 1 or the probability of 0 will be very high. This is called actually qubit. Here we are saying using the term bit. Here we are using the term qubit. So actually what happens that unlike your classical computer, here if it is one the arrow is like this, you can say that it is 50-50 chance. Arrow is like this, you will say it is 50 or 50% or 50% chance. If you suppose it is like this, that means 80% is towards 0, or 15% chance is for getting 1. So this is the thing, or maybe that suppose this is the case, so it will be 80%, 85% towards 1, or 15% towards 0. So but the thing is that you will be getting either 0 or 1 when you will measurement. I will come later after that. So this is actually called the superposition of states. So, so some probability always is there for 0, some for 1. But the important concept is that is what entanglement means when 0 and 1 both, you cannot if we consider this, you cannot get the independent probability of the qubits. That is very important. So together 0 will maybe that the probability is 25% or 0.25. 0 1 probability is 0.1. 10 is zero point 0.4, or 11 is 0.25 probability. So you cannot separate this. Even if you want to try to change this one, it will affect the other one also. So in totality, the whole system will be affected for. So the qubits are no longer independent of each other. This is very important thing you should keep in mind. So another important thing is that is what is called interference. Interference means suppose you are throwing a stone in a pond, so you will find some waves, right? So if you find in some places when two waves will merge, you will find the constructive wave. If it is opposite, then you will get the destructive wave or destructive interference. So that is what is called constructive or destructive interference. That property also holds good in quantum computing. So I was telling about the entanglement or all this. If you see this video, it will be more clear.
Mechanics shows us that reality is merely an illusion. It has been more than 100 years since we started decoding the universe at the tiniest scale. Over the years, we have discovered several intriguing phenomena in quantum physics, but the most interesting is quantum entanglement. This is such a mind-boggling reality that even Albert Einstein doubted its existence. He called it spooky action at a distance. To get an idea of how quantum entanglement works, consider this simple example. Suppose you have a pair of gloves, and you place two of them in two different boxes. After that, you shuffle the boxes and ask your friend to open one of the boxes. If he opens the box and finds a right-handed glove, then without opening the second box, you know that it contains a left-handed glove. This will remain true even if you take the second box to the moon or anywhere in the universe. That's because the two gloves were entangled entities and had a connection between them. One was right-handed and the other was left-handed. But things become spooky when you try to apply this principle to particles in the quantum realm. Particles have an intrinsic property called spin. Before you measure it, it can be in any direction. To measure the spin, first you need to specify the direction in which you wish to measure it. If you want to measure it horizontally, then the two possible outcomes will be left-handed or right-handed. If you wish to measure it vertically, then the two outcomes would be either up or down. Consider the spin of two particles. As mentioned earlier, before measurement it can point in any direction. Let's now measure the spin of one particle along the horizontal direction. Then the measured spin will be either right or left, each having a 50% chance. Even if you select the second particle for measurement, you will get the same results, 50% right and 50% left. However, if the particles are entangled just like the gloves, see what happens. If you measured the spin of the first particle and found it right, then the outcome of the second particle will be 100% left. So, the information of measurement got to the second particle the moment the first measurement was made. And here's the spooky thing. This information is transmitted instantaneously. If you make the measurement in one part of the universe, the quantum information can be sent to the entangled particle instantaneously, even in the opposite part of the cosmos. Remember, traveling at 300,000 kilometers per second, light is the fastest thing in the universe. But quantum entanglement is independent of it. So far, it was believed that quantum entanglement is purely a quantum phenomenon. However, scientists have recently observed this spooky action on a macroscopic scale. Entanglement is actually a correlation between two things. In the experiment, two teams of scientists crafted two aluminum drums of a red blood cell size. Each of these drums has roughly 1 trillion atoms. They placed them on a crystal chip and supercooled the setup to near absolute zero. Finally, they hit both the drums with microwaves. Struck by the microwaves, each drum vibrated, rising up and down by about the width of a proton. This minuscule motion was detectable as a change in the voltage of a circuit connected to the drums. When the drums are entangled, their amplitudes will be correlated. If one drum is measured to have a high amplitude, the other must have a low amplitude. The experiment was set up so meticulously that there was no way the drums could communicate with each other mechanically. The microwaves served as the intermediary that lets them talk to each other. You might be wondering what the purpose of such experiments is. As things become large, they no longer exhibit exotic quantum behavior. The goal of such investigations is to bring something big into the quantum realm. The applications range from quantum computers to problems in physics that require subatomic precision, such as the detection of dark matter or gravitational waves. But perhaps the most compelling aspect of the work, beyond any applications, is that it simply brings us closer to the true quantum nature of the world.
So I think the concept of entanglement is clear. So now another very important thing, that is decoherence and noise. So actually, always the here you know that if there are two qubits, they will always try to entangle with each other, and even they the major problem is that they will always try to interact with the outside of the world, so that will result leaking away of the information. That is what is called the decoherence. And the radiation, cosmetic waves, phone calls, heat, all these things creates the noise. That is the major problem. So this is the very challenging task, that how we will create the qubits with managing the decoherence and the noise. Till now IBM is capable of designing the 433 qubits quantum computer, but they are keeping it in minus 273 degree centigrade. So if this is the situation, then it will be very difficult for the normal person to use the quantum computer. So this is very challenging task. Recently, one scientist from Kolkata and other from which state I cannot remember, US or somewhere. Together they have created the 8 qubit quantum computer, but that is even that can work in normal temperature. That is fine, or normal environment, without getting affected by the uh, other qubits or other environmental problems or noise. But the problem is that the number of qubits is very less. So that is the very challenging task for designing the quantum computer. So this is the thing that this is the history of quantum computer, that in 1980 that Paul proposed the quantum mechanical model for of the Turing machine. You know what is Turing machine. So after that, Richard Feynman in 1982 he has published the paper that he throws an open question to the computer engineers, that how do you deal with the probabilistic aspect of the quantum machines. Can you simulate the physics things in computer, because computer is normally we do the discrete kind of things, but in nature or other things you will find so many physics, so many things which are not discrete, which are in contiguous in nature. So this is the open challenge Feynman given in 1982. In 1985, David this was suggested for a comprehensive framework for the quantum computer. In 1986, Feynman again introduced the early version of the quantum circuit notion. In 1998, first 2 qubit quantum computer was created for the computation by Chuang Nell, and Grover. I told you that whether it is possible to search an element from the array less than n times, linear search or binary search, we all know. But covert search algorithm gives you the you can search any number, any element with root n times. So time complexity order of root n. I told you that whether can you factor the big numbers. So Peter showed in 1994 gave us the way that how we can factorize the large number. How can I get the large prime factors of a number? But if it is, I am telling you that till now 433 qubits quantum computer has come. IBM have developed it, but if it is more, maybe that more than 1000 qubits, which IBM has told us that in 2020, by 2026 they will try to bring the 1000 qubits quantum computer. If it comes, then it will be really a threat for the RSA encryption. In 1992, Luis Josa gave the first algorithm that shows how the quantum computer is faster than classical computer, how quantum computer will help the people to do any computation much faster than, or exponential time faster than the your classical computer what we are using right now. So for developing quantum computer, I am not going into the details because time is very less. Only the things we have to keep in mind, that the number of qubits, as I told, that one qubits affects the other qubits. So number of qubits, if you increase that, then the problem comes more, the error becomes more. Error rate for creating a qubit is very important thing, especially crosstalk between the qubits is very important. We know that connect network is very important thing for us, but when they are getting connected, then the more problems comes. I am not discussing in details due to the lack of time. Systematic error, it actually it depends on the directions of this. I will if we get time other day we'll discuss on this topic itself. But overall, that if I say that if we use the quantum computer, it will increase the efficiency of any computing. So for details, you will get this link also is given, you can get it from here also. So this is found from the Google blog, that is implement the error corrections. It proves the error correction gets better with increase in the number of qubits. As already I have told, their concept is first generate the one qubit, then two qubits, and then you increase to thousands qubit. That is what is the approach that Google is following while designing the qubits. So this is the latest development by the different companies. As I told, that IBM is in 2022 for 33 qubits. They have already given. 2024 they plan to give the 1000 qubits, but not yet. I think by 2026 they will give it. This is the update. Google, as I already told, that they are in 2021 they have claimed that they have built the quantum device successfully to resolve the problem faster than the fastest supercomputer. But again, I am telling that they could not reach to as IBM, that is 433 qubits processor. They could not able to give it. There are other companies, QCI, they have released SaaS computer, cloud computing environment. All these things are there. I am not going into the details. So these are the Microsoft, Azure Quantum, DOA system. All these things have been developed till date. But it is, I am again telling you that it is in the infant class kind of things, means there are lots of scope for doing research. You know that recently our prime minister have announced 6000 crores for the research in quantum computer. They have probably set up four quantum set up in four zones in India, different zones. That is what is the planning. So this is the thing. So there you have a huge research scope in the quantum computer. This is very common double slit experiment. That is the question was that whether it is a light is wave or it is a particle. So there are the double slit experiment says that when you are sending some lights, if there are two slits, then you will be getting in the waveform waveform. But if you block one slit, then you will get as a particle form. If you measure, you will get the this waveform nature will be destroyed at all. So actually, the we have to know two three terms. That is, one is called Hilbert space. In real space, what we use XYZ axis. In next slide we will show you. But here actually there may be more, and even there may be that the momentum, spins, or polarizations of particles. All these things are there. So if you want to deal with the nature things, Hilbert space you have to follow for dealing with the wave functions. But the important thing is the measurement. When you will try to measure, it will totally collapse. That means either you I have told you now that the probability of 0 will be 0.85, or maybe that probability of getting 1 is 0.15. But when you will measure, you will get either 0 or 1. So that when you measure it, then it will totally collapse to get the classical bit. So actually in 1958, the Dirac have proposed the bracket notation. Bracket means it is written in this way, this symbol, then bra, then ket. So actually for 01 we write in this way, uh, the bra, then 0, then 1, then ket. So this is the symbol of bracket, the notation of bracket which we used here. As I told you that for representing any vector A, we represent it in this way, that A vector can be represented in as ax I plus b ay j plus az k. where I, j, and k are the basis vectors or unit vector, you know. So if I perform the dot product of ii, and if ii equals to j dot j or k dot k, if it gives 1, it is called normalized. If it is if I dot j equals to j dot k equals to k dot I equals to 0, then it is called orthogonal. In Hilbert space, actually, suppose if you span by the psi 1, psi 2, and psi 3, then psi is represented as c1 psi 1 plus c2 psi 2 plus c2 3 psi 2 psi 3. Actually, that means actually if you perform the volume, actually not single integration, you can put another integrations also. So this will give you the delta ij, and if delta ij, that is actually called brackets psi ij and psi I psi j. That means if psi I psi j equals to 1, it happens. Then if I equals to j, if it is 0, then I, if I not equals to j. This is called orthogonal or normalized property. I am not going into the details of the mathematics due to lack of time, but in simplicity I can say that, like the last slide, that if I represent alpha ket0 plus beta ket1, alpha beta are the probability of getting 0 and getting 1, then we represent 0 like this. We represent we represent psi, suppose this is psi equals to this. We represent psi as with this matrix, that means alpha beta. So alpha getting 0, the probability is alpha, and getting 1, the probability will be beta. And 0 matrix 0 ket 0 is represented as matrix 1 0, and ket 1 is represented as ket 0 1. So this is the Dirac notation for representing the vectors in quantum mechanics, and it follows the all the rules of linear algebra. If I write 2 into this, then you can easily write this one as 2 alpha ket 0 plus 2 beta ket 1. So, or in matrix form 2, then alpha beta it can be written as 2 alpha 2 beta. So this is the thing which we, it follows the, or even other properties of linear algebra also is being followed. Okay, so actually for you can design it with the polarization of the photon or the spin of using electron. If suppose if we consider polarization of photon, then this up arrow, actually the vertically polarized photon will give you say 0, and this one will, or horizontally polarized photon, that will give you 1. Similarly, for if you consider the spin of an electron, if it is up arrow is giving you the vertical spin, that is you may consider as ket 1, and if it is down arrow, then negative vertical spin, that you can consider as ket 0. So in this way we represent it. So here up arrow, down arrow, that is 1 or 0 actually are the fixed basis, and we represent, as I have told, that ket psi equals to alpha ket 0 plus beta ket 1. That means alpha and beta are the probability of occurring 0 or occurring 1 respectively. Always you should keep in mind that alpha square plus beta square always will be 1. This is a probabilistic value. As I told you, the probability of getting 1 or 0, or probability of getting 1, if it is alpha beta, then alpha mod alpha square plus mod beta square always will be 1. Superposition, as already told, superposition of the qubits is just a fancy term of the linear combination, nothing else. So if you consider two qubits system, then two qubits means you can consider two up arrow that you may represent as you can say that as ket 1 1, up arrow down arrow as 1 0, and down arrow up arrow means 0 1, and down means 0 0. So if you consider 2-qubit system, the psi can be represented as A, then down down, plus beta ket down up, C ket up down, and D ket up up. Or in simplicity we can write psi equals to A 0 ket 00 plus B ket 01 plus C ket 10 plus D ket 11. And as I told that always alpha square plus beta square plus a square plus b square plus c square plus d square always will be 1. And this is complex vector space. Already I told that linear combination of all possible values for two classical bit you will be getting, and it follows the all properties of linear algebra. So if we consider 2-qubit system, this is actually called tensor product. 0 tensor ket 0 tensor ket 0, that you can write as ket 00, ket 0 ket 1. If you perform the tensor product, you will get 0 1 1 0, you will get 1 0, or 1 1 if you perform the tensor product you will get 1 1. The thing is that this 0 0 is represented as 1 0 0 0. How we are getting? As already I have told that 0 is represented as this 1 0. This 0 is represented as 1 0. So if you perform the tensor product of these two, tensor product means this one will be multiplied with this 1 0. Again this 0 will be multiplied with this 1 0. So that means 1 1 you will be getting 1. All other cases you will be getting zeros. So in this way you are getting this one. Clear? So ultimately 0 0 0 1 1 0 and 1 1 we represent using we can calculate using the tensor product. And interestingly, if you write together you will be getting I4, means you are getting unit matrix. You are getting unit matrix. So unit matrix is very important for quantum computer point of view. I will come. So I have told that 1 qubit, I have told 2 qubits. If it is n qubits, that can be represented as summation of k equals to 0 to 2 to the power n minus 1 ak ket 0 ket k, where same as a square b square plus a square plus b square plus c square plus d square here, up to similarly a0 square plus a1 square plus a2 square, similarly up to 2n minus 1 terms, 2 to the power n minus 1 terms, it will you will get the result as 0 a 1. So this is the thing. So n qubit can be represented like this. As I told that if you want to measure classical bit, you are getting 0 or 1, but if in quantum it is not, it is a probabilistic value. But if you measure, then you will get either 0 or 1. For example, suppose there are 3 chairs, and uh, your probability of sitting in some chair is something, maybe that sitting in the chair number 1 is zero point 0.4, chair number 2 is 0.25, and chair number 3 is 0.35, total 1. But when you are sitting in some chair, then it is meaningless to say that probability of sitting in this chair is point something. No, you are sitting, or you have, when you are sitting, that means all other states will be probabilistic value will be nullified. That means you are sitting in that chair particularly. Here also, when you are until you are measuring, it is okay. But you, if you try, when you are measuring it, it will be collapsed. So this is the beauty of quantum in measurement. Okay, so that what I was saying, that alpha ket 0 plus beta ket 1. Suppose it is giving ket 1, ket 0. That means the probability will be alpha square. For getting 1, the probability will be beta square. But when you are measuring, there is no existence of other. Now, For quantum wire, you know that in classical there are different gates. For example, AND gate, OR gate, NAND gate, NOR gate. But here, the gates are slightly different. How? If you pass zero, actually zero over here, if you pass suppose 0, you will be getting 0. If you pass 1, you will be getting get 1. Okay, this is the thing. So if you pass a 0 get 0 plus b get 1, you will be getting this thing. Actually, you will be getting a get 0 plus b get 1, which you are passing in the quantum world, you will be getting same thing. But X gate is like your NOT gate as you have used in the classical gate. If you pass 0, you will be getting 1. If you pass 1, you will be getting 0. This one. Suppose you are passing 0, you will be getting 1. If you pass 1, you will be getting 0. If you if it is A get 0 plus B get 1, you will be getting A get 1 plus B get 0. It is represented in the matrix that if it is 0, you will be getting 1. If it is 1, it will be getting 0. So this is the matrix that you will be getting. As I told that 0, if you suppose you are passing through X gate, it is written like this. So if you simply multiply this one, I have told that X gate multiply this is the matrix, you should remember it. So if it is x0, that 0 you know, as already I have told, it is 1 0. So if you multiply these two matrix, very simple, you do the matrix multiplication, you will be getting 0 1. That means you are getting 1. Similarly 1 1, you know, matrix is 0 1. So if you multiply these two matrix, you will be getting 1 0. So that means get 0. This is how the NOT gate or X gate rather, actually we use the term X gate, works here. Now can you tell me, if we two X gates are there, suppose you are passing 0, what will be the output? It will be 0 itself. Not of 0 means you will be getting 1. 1 of 0 means you will be getting 0. That means same as quantum wire. If it is A get 0 plus B get 1, then you will get A get 1 plus B get 0. So again, if it is X get, you will be getting this one will be 0. So A get 0 plus B get 1. Clear? If we want to solve the problem from mathematical point of view, Xx means what? This matrix and this matrix. If you multiply, you will be getting this I. Right? That means the effect will be nullified. If it is psi, x psi, xx psi, that means I psi means psi. This is how the quantum X gate works. So using matrix, maybe that some people may say that we have done matrix in class 11 12, we have forgotten. So even without knowing the matrix also, the problem can be resolved. How? You should remember that X can be represented by this ket 0 bra 1 plus bra 1 ket 0. So if X of ket 0, that means you this one along with 0. So what will happen? Ket 0 ket 0 bra 1, sorry, along with this one, that means 0 plus 0. So bra 0 ket bra 1 ket 0, this will be 0, but bra 0 ket 0, it will be 1. That means from here this part 0 means this one will not come, but here 1 means you will be getting ultimately 1. So in this way also you can easily you can calculate what will be the result. Similarly for y gate actually the matrix is 0 I minus I 0. So always I am telling you, if you multiply y and y again, you will get unit matrix. J dot z, you will get unit matrix. So y is represented as this. Phase I means phase change. So y can be represented as this. So y of 0 means I of 1. I of 1 means, sorry, I should say actually I get 1 rather. Y get 1, if you perform, you will get minus I 0. That means there will be a phase change. Now for Z gate, actually Z gate can be represented as this one. So in similar way, if you perform on the 0 qubit, then you will be getting 0. If it is 1, you will be getting minus 1. So these are the basic 3 gates which are known as Pauli gates. So there are some simulators. Uh, I think we'll show at the end of this lecture. So if you consider 0 gate 0, and if you consider the X gate, then here you will be getting gate 1. What is the probability? Probability is 100%. So probability is 100% to get 1. Similarly, if it is 1, you will be getting 0 with 100% probability. Okay. Similarly for Y gate, I told that if it is 0, you will get 1, but there will be a phase change. 1 I. This in complex, I have told that complex number is represented, that A plus IB. So this is there will be there will be no phase change for if it is 0, but if it is 1, there will be a phase change, that minus, it will be minus I actually. So there will be a phase change for 1, yeah, get 1. Similarly for Z, if it is 0, you will be getting 0. If it is 1, this one will be minus 1, but this one will be 0. Probability is 100% to get 1. Very interesting gate is that is called Hadamard gate. That is actually real quantum gate in terms of superposition. If you pass 0 over here, you will be getting 0 get 0 plus get 1 by root 2. Superposition of 0 and 1. Very interesting. If you pass 1, you will be getting 0 minus 1 by root 2. What is the matrix? This one is the matrix. So A0, A ket 0 plus B ket 1 will give you this thing. Just putting the value. In place of 0, you have written 0 plus 1 by root 2, or 1, 0 minus 1 by root 2. So if you do the simplification, A plus B by root 2 0, A minus B by root 2 1. Okay, so as I told that if you want to avoid the matrix multiplication, you have to remember this thing. So if you apply Hadamard on 0, very simple. In using matrix, you can put the matrix, you can multiply with 1 0, you will be getting 1 1. That means 1 by root 2 get 0 plus 1 by root 2 get 1. Similarly for 1 only there will be a negative sign, this negative. Interesting thing, will it give you the I if we use 2 atom? The answer is correct. H always will give you I. Psi H of psi, H of psi, H always will give you I. You can use the matrix, you can perform the matrix multiplication, you will be getting the unit vector, right? 1 0 0 1. If you multiply two matrices of same matrix of atom. So if it is 0, previous I have told that for Hadamard getting 0 or 1 is 50-50 chance. You can get either 0 or 1, or 0 plus 1 by root 2 or 0 minus 1 by root 2. So you will be getting the 50% chance of get 0, 50% chance of get 1. What is the probability? 1 by root 2. 1 by root 2 means what? This one. Okay. Similarly for 1 also, 50% chance of getting 0, get 0 and get 1. Probability 1 by root 2. But here minus 1 by root 2, that is why the minus sign is there. Similarly, if you perform 2 Hadamard, see, 1 Hadamard actually it will give you I. That means you will be getting 1. What is the probability? 100%, not 50% like previous one. Because 2 HH will give you I. Similarly on 0, you will be getting 0 with 100% probability. Okay, so these are the things you can practice for. Obviously HH will be what? I so 0 when we will pass through 1 x, what it will be? 1. 1 when it will be passed through x, z, what it will be? Already you know. If you passed 1 through z, you will be getting minus 1 at 1. So this is the thing. Similarly, you can pass 1 through y, then x, or z, then x. You will get the result. Okay. The time is 1. I think I will not discuss only one thing. This one I can say, as I told that it is it accept all the properties of linear algebra. So if it is alpha beta, so that can be written u then alpha dash beta. For example, I have told that if it is suppose 2 alpha 2 beta something like that, 2 can be taken as common. This is actually u. And for unitary matrix, u dagger u equals to I, as you know from the linear algebra. So u dagger is actually equals to u transpose then conjugate. So this is the thing. So if it is A, B, C, D, this is the matrix. If you perform u dagger, you will be getting A conjugate, B conjugate, C conjugate, D conjugate. This is as a result. So this is called actually unitary matrix. That means if X matrix is this one, X dagger will be this one, such that X dagger X equals to I. Similarly, if you consider H matrix, then H dagger will be this one, equals to H. So H dagger H equals to I. You can see the same thing for Y gate. You can see the same thing for Z gate. Okay. Okay, just I want to touch this thing, then I will Swap gate. Swap gate actually, you know that if it is AB, it will be swapped. A will come here, B will come here. That means you will be getting BA, get BA. If it is 0, 0, you will be getting 0, 0. If it is 0, 1, you will be getting 1, 0. If it is 1, 0, you will be getting 0, 1. If you will get 1, 1, that means it will be 1, 1. Right? So, what is the matrix of 0, 0? Already we know 1, 0, 0, 0. 0, 1 means what? 0, 0, 1, 0. The next one, 1, 0 will be swapped. So it was 0, 0, 1, 0. I am showing you once more. Actually, this one was previously it was 0, then 1, then 0, then 0. And this was 0, 0, 1, 0. So if we swap these two, what will happen? You will be getting this one and you will be getting this one. Clear? Because 0, 1 and 1, 0 will be swapped. If it is 0, 1, you will be getting 1, 0. If it is 1, 0, you will be getting 0, 1. So that means if it is 0, 0, if it is 0, 1, 1, 0 and 1, 1, so these two positions will be swapped. Rest will be same. So that is what is the task for swapped gate. So if it is swap gate, if it is 1, 0, this will be 0, 1. If it is 0, 1, it will be 1, 0. But if it is 0, 0 or 1, 1, it will remain same. That is what is swap gate. So if you, okay, so I am not going into this part because it will be more interesting if you see some hands-on, because time is only 25 minutes is left. So I am not going into the rest part. Achha, this is another thing. C naught. C naught means it depends on if this one is 1, then only it will be changed. How it is? Let me. We will show in the labs hands-on session. C naught session. Leave it for the time being. Yeah, we are closing here. I think it would be better if we go for the lab session. I will request Showman, one of my research scholar, will show you the hands-on. After that, if time permits, I will explain all these things. C naught, CC naught, I will discuss on these things. Showman, are you here?
Yes, sir. Am I audible?
Show the simulation part, and then if time permits, we will go to the rest part because only 25 minutes is left, what I find.
Yes, sir. So am I audible, everyone?
You share the screen? I have closed already.
You can hear me? Am I audible?
Yes, yes, yes. Continue.
Yeah. Just one second. Just to need to connect the. Yes. So I'm just sharing my screen. Is it visible? So basically, what we will be doing is, so there could be many kinds of simulators. So the thing is, as we don't have real-time quantum computers in our hand right now, So what we can do some simulations. Now there could be several types of simulations, especially IBM or Google or um, other companies like Microsoft. They also provide some kind of simulators and some kind of practice with simulation. And also you can access their quantum computer via cloud platform. But those things can be a bit difficult to access on. So right now we will be using this GUI simulator, and it will be an easy one to do, easy one to practice with everyone. If you want, I can just give open source simulators link in the chat box. You
I think
can,
you give the link and everyone can open and they can do parallelly. It would be better.
yes, sir, I've
At
done.
least two problem they can do parallelly.
Yeah, so this is the link you can use right now. So for practicing as well. So we'll be just going through the some of the gates, whatever you have learned, and this is quite an easy simulator to use. So this is what you
First,
can do.
let them give some time to open that simulator.
Yeah, yeah. You just
You,
open the simulator.
you show them to open it.
Yeah, you just paste the link on the bar, and you can easily access it. Can I start?
Yes, sir.
Yeah. So now you can see here is the option of circuit. So in this circuit, we can basically change the number of qubits. So first, let me give some introduction about it. So these are the things you can see over here. These are the qubit registers, or basically you can simply call it as qubits. So this is one qubit, this is another qubit, and these are the states of the qubit which we can change. So we'll simply start with a single qubit system right now. So you can go to this circuit option. You can see, you can change at least for this simulator. You can go up to,
Let them you do it. Other also can do parallelly, at least for the first problem.
so you go to this circuit section and you can see the number of qubits you can change here like this. From 1 to 10 qubits you can, at max you can use. So the number of qubits right now you can set it to 1 to just to change, check the for one single qubit gate, it's single qubit gates. So this is the single qubit you can see right now. This is the qubit register. For simulation purpose, you will also use the term called single wire or a qubit wire, or you can also, for simplicity, you can use the term qubit. And this is the state of the qubit. You can see right now it is state 0. So if you want to change the state of the qubit, you can simply go over it and click it. By clicking this particular state, you can change the state from 0 to 1 and 1 to 0. And you can see right now I'm not using any kind of gate. So the task here for this simulator is to understand whatever the output is coming, whether you can read and understand the output, the output actually what is coming along with the state and the probability. That is our task. And the thing is, now right now it is just a qubit wire, as you can see, qubit wire. So no gate is put. You can simply run this circuit by control enter. In your keyboard, you can press Control and Enter. You can simply run the circuit. And if you run the circuit, now you see this is how the output is coming. Now, how you can understand or interpret this output? That is the task. So right now you can see over here. So first, I'm just right now you can ignore this part, whatever I am saying, or whatever I am saying that this is the state. Ignore this particular marked part. You can simply see it is showing 0. Means the 0 state I have given as input and the 0 state I have got as output. And output is 100%. It is showing the output probability 100% because there is no superposition of the state, only single state is there. So there is no chance of occurrence, no chance of occurrence of any other state. You can simply get the state whatever you have given. And you can see right now there is the I component, means the complex vector component, that is 0. Multiplied with 0 means there is no complex component. So I hope you remember the matrix of 0. If you can see the matrix of 0, it is simply 1 0, the column vector 1 0. So there is no I component or complex component. So that is why it is there is no I component or complex component is present. And 1, so this 1 is only validated, and this 1 is the amplitude, or you can understand 1 is the 100% probability. 1 square means 1. With full probability, 100% probability, the state 0 exists. This is how you can interpret the output. I hope it is clear how you can study the output, how you can interpret the output for this simulator. Similarly, if you I just change the qubit state from 0 to 1 and then I run it, now you see everything is same, only the state has changed from 0 to 1. So 1 is the input and it is a quantum wire. There is nothing gate working on it right now. So this is simply 1. Now let us just try
Have you
with
done
the
this? All of you, have you done this? Could you able to do? Anyone is facing problem?
the only job here is to understand how to read the output, how to interpret the output. I hope it is clear to everyone.
If anybody is having
Yes,
doubt,
sir.
yes,
Yes.
very good.
Now let us just start with the single qubit gates. So this is the X gate or the NOT gate, quantum NOT gate, as you have understood. So the quantum NOT gate I am putting on this particular qubit register. This is the X gate or NOT gate. Now NOT gate means what is expected. 0 will be the input to this gate, and as output I will be getting the state 1. So if I now simply run this circuit particularly, now you see it is again showing 1, and as there are no superposition, so there is no sharing of the probability. Right now it is occurring with 100% probability, as you can see over here. And there is, as you can, if you remember the gate of the NOT gate, what is the matrix of the NOT gate? What is the matrix of the NOT gate? It is simply just converting 0 to 1 means 0 1, and 1 to 0 means 1 0. So there is again no I component or the complex component over here. So that is why again the I component is not present. Only the uh, real-time component, which is the 100 amplitude, is present over here, and with giving 0, I am getting the output 1. Similarly, just by clicking on it, you can change the quantum state. Now it is 1, and now what is the expected output? It is not gate, so it is going to see the output is now changed to 0. Means I am giving 1 as the input to this X gate, and I am getting 0 as the output of this gate. Now I think the other ones nothing changed, so you can read easily understand the things already. Got it? Everyone? Now, by just right clicking over the gate, if you right click over the gate will be vanished, and you can use a new gate. By selecting the gate, click on it, you come back, click back on the register, and the gate will be put. Now, if I try to use the Y gate over here, and for Y gate, I think if you again could try to recall the matrix of Y gate, now there is something, the complex component, the I component is present over here. And now if I simply run it, or let me first run it to 0. Now you can see the state has changed to 1. Now, if you remember the matrix of Y gate, it is 0I. When you give input as 0, it is 0I. Now, 0I means you can compare it with the matrix of 1, which is 0, 1, means it is the state of the 1 state. If the state is 1, 0I and 0, 1 only differs in the I component, nothing else. So if I just consider or take this I out as the amplitude, you see the I component is right now present over here. That is why it is 1 into I, and the real component is not present here. So 1 into I, but the state exists at 1. So that is why this is the difference of the X gate and Y gate. Again, if you give 0, it will give 1 only, like the X gate you have seen already, but it is not the real component. The imaginary component I is present over here. That is why it is showing 1 into I, then the I state, means the quantum state, which is the output state, that is 1. And again, probability 100% will be same because there is no superposition. Unless the superposition comes into picture over here, the same thing will be present like this. And if you now change, compare with the matrix, it will be changed to 0. Means if you remember, it is minus I0. The vector for I matrix or Y matrix, it is minus I0. Means the imaginary component minus I will be taken out. 0 will be simply present over here, and it is 0 state, and it is minus I. and it is simply the output is zero state. That is the difference between X gate and Y gate, just the I component, so the complex component, nothing else changes. Now, again, if you remove it, and if I try to use another single qubit gate, which is known as the Pauli gate, or another Pauli gate, which is Z. If I put Z here, now while I am using the Z gate, in Z gate, if I give the input 0, nothing changes. So with the input 0, Z gate simply produces the input state 0 only. And again, if you remember, there will be no, in the Z gate also, there is no I component or complex component. It is not present over here. Simply the real component is present with 100% probability. And my input state is 0. There is no change in the output state. For input state 0, the output state remains 0. That is what is done in Z gate. But the thing changes in Z gate. In Z gate, if I just change the input state to 1, for one input, the phase shifts, the phase changes for Z. So for Z, now it will be -1. As you have seen, it is 0 -1. Now -1 means nothing else. The output state will be 1 itself, but the component, the real-time component, whatever you were seeing right now, it was positive. No, now it is not positive. It has turned to -1. Means it is now a negative component. That is why. It means the phase has changed. So 1 was there, now it has just shifted. Nothing else. The phase has changed. That is why the minus sign has come. Nothing else. So for 0 basically, for Z basically, 0 gives 0, 1 gives 1 as output state, but only shifts the phase or changes the phase. That is the difference. That is what is done in the Z gate. It is a pretty simple gate and it is used for phase changing in many quantum computing applications. Now, another single qubit gate I will be using, that is called the Hadamard gate, and which is also known as a true quantum gate. True quantum gate in the sense, now in the last few gates, whatever you have seen, for whatever you have seen in the last three gates, X, Y, Z, there is no superposition created. For every state, you are getting a definite output. For the definite output, and so that is why it is every time it is you are getting 100%, and for 100% means there is no superposition. Now if we use the Hadamard gate over here, now try to recall the matrix of Hadamard, or the input state or output state of Hadamard. If I give 0, you are going to get 0 plus 1 by root 2 as the output state. Means 1 by root 2 is the amplitude for both the states. 0 plus 1 means in linear combination, both the states are present. 0, 1 by root 2, if you square it, half means half 0, half 1 means 50% probability of 0 and 50% probability of 1. Now, if I simply run it, you can see 0 state is present with 50% probability, as it is 1 by root 2 square is half, that is the probability. 50% with 50% probability, the state 0 exists, and with 50% probability, state 1 exists. Now, there is no I component in the Hadamard as well, but you see the amplitude here is 0.707. Means what is 0.707? You can calculate, it is the value of 1 by root over of 2. 1 by square root of 2, that is 0.7. So with same amplitude means same probability, we say 0.707, both the states 0 and 1 are present. And that is why Hadamard is known as a true quantum gate. In the last few gates, we have not seen any kind of probability distribution is dividing in the states. No, there was definite output for the states, which was 0 as well as 1. Now, where in the Hadamard gate, if I give input of 0, you are, excuse me, you are going to get state 0 and state 1 with same probability, which is 1 by 2 or 50% simply. And now for the input 1 to Hadamard gate, what happens? Everything remains same, but the thing is, it is 0 minus 1 by root 2. Means if I take 1 by root 2 out, again the probability will be means 1 by root 2 square means 1 by 2 means 50%, but 0 minus 1 means the existence 0 will be here like this only, and for 1 this thing gonna change. It is minus 1 by root 2. Because it is 0 minus 1 by root 2 means minus 1 by root 2 means it will be minus 0.707. If I simply run it, you can see it. Means again the superposition remains. So if the superposition remains, means 0 and 1, both the states are present with 50% probability, and 0.707 for positive 0.707 for 0 state, which is half,
Already
and
we have
negative.
told, so man, time is very less. I think you try to show some 2 qubit system also, a small example.
2 qubit system, I think Sarvani will assist with us. So
Yeah.
both of us
So
will.
you
So I can. I can give it to Sarvani.
Yeah, yeah, it is
Sarvani?
better. Time is very
Yeah.
less. Just we are giving the
Sure.
overview to all. I am telling you that it is not possible. We understand that within the short period, but if anyone is interested, they can communicate with us anytime regarding the detailed discussion. So, Sharvani, please.
Sarvani,
Yes, sir.
please. What?
Yeah, presently. Is it visible? My simulator page?
Yes, yes, you continue.
Okay. So moving to the 2 qubit gates, if we have already seen the 1 qubit gates. Now just a simple circuit with a 2 qubit gate. If we take 0 0 as our qubits, and we are putting just not, I mean, the x qubits here. So we will have this 0 will be 1, and this 0 will also become 1. So we are getting output as 1 1 altogether. Okay, and here also the probability is 100%, right? So next, we if we see, like, if we just see with this, we are having just one x gate here. So what will be the output? This 0 will be converted to 1 due to this x gate, and this 0, it acts as a quantum wire here. So we will have 0 and 1, right? So this 0 will become 1, and the next qubit will just remain same, that is 1 0, with again with 100% probability, right? Now if we see some Hadamard gate here, sorry, Hadamard gate we have already seen. Let us see some C naught gate. Now how to build this gate on this simulator? Just first select this X gate, put it here, click it, left click, and then select this control gate. You just drag it from here, we will have our C naught gate. Okay.
See, not actually, I have not told.
Okay,
Just a
yeah,
little
yeah,
overview, just then.
yeah, yeah, yes, I will tell. So C naught gate is a gate. It's a 2 qubit gate which has a control qubit and a target qubit. This is the control qubit, and this is the target qubit. Okay, so control qubit will, I mean, the target qubit will be changed. This is not gate, as we have already seen, and this is the control qubit. So if the control qubit is 1, then only the target gate, the gate in the target qubit will act. So if this is 0, so this gate is inactive. This won't this gate will not be working. We can see, we can check the output. See, if you press enter, you can see that it is 0 0. This gate is not acting. Okay, now if we change this qubit to 1, and then we press enter, we see that this gate, this is active now. This gate is active, and this not gate will be acting on this qubit. This 0 will become 1, right? We are having, this is 1, and this is again 1. So we are having 1 1 with probability 100%, right? So this is the gate. This is a basically C naught gate is one of the gate which creates entanglement, as we have already seen what is entanglement. So entanglement is created using this C naught. More interesting things are, if we try with different many other gates, the more the number of gates, the more interesting will be the circuit. So now we can see the output. We can check the output. Now see, this one is 1. So X gate, due to X gate, the 1 will become 0, right? And since this is 0, again the gate is inactive, because the target, the control qubit is again 0. So this gate will be inactive. So this the output will be 0 and again 0. See, 0 and 0. So we can try with various gates here. Now see, if we are having Hadamard, we can see this gate will be acting, and then again, and then 0 0 and 1 0. We know that 0 0 plus 1 0, I mean, not on this will be create will we will have 0 qubit here. If we check this state, one second, yeah, if we check the state here, I mean, after the X gate, we are having 0 here in the first qubit and 0 in the second qubit, right? After that, this gate will act. This is, since this is inactive gate, so we can ignore this gate, and then we will have Hadamard on the first qubit. The second qubit will not change. So we can see we are having 0 0 0 1 0 with probability 50% and 50%, right? And this is the amplitude 1 by 2 1 by root 2 1. So this way we can see various other, we can
On the
create
same circuit, you just change that 1 to 0.
yeah.
Yeah, then explain again, it will be clear to
Yeah.
everybody.
Now, if you're changing this qubit from 1 to 0, then you see due to this X gate, 0 state will be 1, right? Will be converted to 1. And then this gate will be active. So what will be the output? This will be 1 and 0 in this state. In this state, we are having the first qubit as 1 and the second qubit as 0. After applying this C naught, we are having this as the first qubit as 1 and the second qubit as 1 again, right? Then the Hadamard gate will again be applied on the first qubit only. So we are having uh, due to this C naught, we are having an entangled state. So we are having 0 1 and 1 1 with, again, due to this Hadamard gate, we are having 50% probability in each of these states. So I hope it is clear now. The two qubit gate. Not only we can work on two qubit, we can work on many other number of various. You can create our own circuit like this, and we can check the outputs. It's very interesting, and I think um, I am able to make you understand what I'm trying to say. So you can check the output. See, there are five number of qubits. So 0 1 0 0 1 0 1 0 1 1 1 0 0. With, again, due to this Hadamard, we are having 50% probability, and all of these two states are entangled. So um, I think, yeah, I have to stop here now. Over
Just
to you.
explain the swap kit. Swap kit, I think it is missing. We have
Okay,
to
okay,
discuss it.
okay. I'm taking two qubits. I'm taking two qubits.
Yes,
Just
yes.
to explain the swap gate, we are taking swap gates here. I'm changing this qubit to first qubit to 1. Then what will be the output? The output will be, it is 1 0, and the output will be 0 1 simply. Yes, with 100% probability. Now again, if you take X gate here, what will be the output? This qubit will be changed to 0 0 0, and the second qubit is 0 only. So our output will be 0 0 again. It's This is the swap gate with the 100% probability. So over to you, sir.
Yes. So I think we could able to give. Even I am telling you, there are other interesting gates also, like CC not also is there. Mm, but we are not discussing all these things because time is already over. So we are closing the session here. But the thing is that if you are interested, you can go through the any standard book of quantum computing, or you can search. Nowadays, unlike the previous days, like right now, different materials are available. So many materials are available in the internet. So if you are really interested, you can go through it, and you can design your own circuit. There are so many challenges. I have told already that it can be just we have given the basic concept of the gates, but actually based on that you can create the qubits, you can denoise the things. So or you can in cryptography there are so many cryptographic algorithm, right, Sarvani and Somen, they are working on that, actually how to break the steam cipher using this quantum computing concept. So these are all are the things. Actually there are so many research challenges are there. So if you are really interested, you can go through it. You can communicate with us. Uh, we are working on this. Thank you. Any other question? Any question from you?
Sir, could you please provide us the PPT or the notes of today's session? It would be
Okay, okay,
helpful.
okay, 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 okay. I will do.
Okay, thank you.
I will
Does
send.
any other participants do have any question? You can ask, sir.
I know that many things may not be clear because actually the things it requires at least 3 hours to give the overview, at least 3 hours or 4 hours. So, what we have tried to show you, we have tried to enlighten you that these are the things. Now you can proceed. Any
So
questions?
then, sir, shall we conclude now, sir?
Yes, 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 yes.
Okay, sir. It will be very helpful if you provide the slides. We can go further for bit understanding.
Yeah, yeah. We will give it. We will give it. I will send
Okay, sir.
you the mail. From that and that I can. I think you can share with all the participants.
Okay, sir. Okay, sir. Surely, sir. So thank you, sir, to give an such an interesting lecture on the topic. And I think our participants have been able to understand or gather knowledge from your talk. We will be hoping to hear you from other programs also in our college. So thank you very much for your expert talk, sir. Thank you.
Thank you, and I would like to thank all the participants for hearing. I think all are the faculty members of different institutes, so we are all in the same bench. So thank you all, and thank the organizer.
So
So
by this, we are concluding the session 2 of our third day, and we will be resuming our last session of this day after the lunch break, and that will be at 2 p.m. And we will notify you through the WhatsApp group to join in the last session where Dr. Jyoti Shekhar Banerjee from CSI Kolkata will deliver his lecture. Please be there at 2 p.m. Thank you.
I am leaving. Okay.